Hello, my name is Marie Callahan for discussing Thevenin's theorem and solving for resistance Thevenin. Thevenin's theorem states, any linear circuit containing several voltages and resistances can be replaced by just one single voltage in series with a single resistance connected across the load. What does that mean? We can reduce a complex circuit with multiple voltages and resistors to a specific node point. This complex circuit can be constructed of parallel and series connections. The goal is to reduce the circuit to the equivalent at the node point for series voltage and resistor. The measurement of Thevenin reduced circuit will be equivalent to the complete circuit at that selected node point. So node points. Where to hang your circuit? Depending on where we're taking the Thevenin resistance of a circuit, our reading will change our resistance. Consider the following circuit. At A, we'll measure node A to ground. At B, we'll measure node B to ground. And at C, we'll measure node C to ground. And at D, we'll measure node D to ground. So starting with node A, we want to redraw the circuit so we can find the Thevenin resistance. So for node A, we begin and notice that we have two branches. R1 at 100 ohms and R2 at 330 ohms. Moving along the 330 ohm branch, we notice that we also have another branch that splits. R3 at 120 ohms and then R4 at 47 ohms that run in series with R5 at 120 ohms and R6 at 330 ohms. From this, we can now work on solving the resistance by pulling out the types. As we can see, R4 and R5 and R6 are in series. We will then evaluate R3, R4, R5, and R6 as parallel, and then R2 with the resulting as another series, and R1 with the previous resulting as a parallel. In our next slide, we'll go over the mathematical equations in solving this. So in finding node A, the Thevenin resistance, we will solve series R4, R5, and R6, which is adding all of the resistances, giving us a total of 497 ohms. We will then take that answer and solve with R3 in parallel. Resulting in approximately 96.66 ohms. We'll then take the previous answer of 96.66 ohms and solve in series with R2, giving us the answer of approximately 426.66 ohms. Taking that result and solving with R1 in parallel, we will have approximately 81.01 ohms. Verifying this circuit in multisim, we can see that the answer is 81.012 ohms. Looking at node B, we need to redraw the circuit. Same circuit, but different branching. Starting from node B, we can see that we have three branches. R2 at 330 ohms, going down to R1 at 100 ohms, we have 120 ohms branch at R3, and R4 at 47 ohms in series with R5 at 120 ohms, and R6 at 330 ohms. As we can see, we'll have two series circuits to solve, and then using those results, we will have a parallel circuit, giving us the Thevenin resistance. So let's find the answer for node B. R2 and R1 solved in series gives us 430 ohms. Solving R4, R5, and R6 in series is equal to 497 ohms. And using both those answers, along with 120 ohms of R3, solved in parallel, will give us the result of 78.92 ohms. Verified in multisim, we can see that this is the answer that we got. Node C. Once again, the same type of circuit, taken at a different point. So we'll begin to redraw node C. Branching out from node C, we see we have two branches, moving to R5 at 120 ohms in series with R6 at 330 ohms. Moving the other way at R4 we have 47 ohms, and noticing that we branch again in parallel to R3 at 120 ohms, and then R2 at 330 ohms in series with R1 at 100 ohms. From here, we can map out our series circuits, R5 and R6, and R2 and R1, as well as our parallel of R2, R1, and R3, another series of R4 between R2, R1, and R3, and then finally the parallel between the result of R4, R2, R1, R3, and R5, R6. So let's solve this one. Taking the result of R5, R6 in series is 450 ohms. Our series circuit of R2, R1 is 430 ohms. Using the result of R2, R1 series and R3 parallel, we result in approximately 93.82 ohms. Using that answer with R4 in series, gives us the result of 140.82 ohms. We can now solve the Thevenin resistance by using the previous answer and R5 or 6 in parallel, giving us 107.25 ohms. Verifying this circuit in multisim, we can see that that was our result. Last but not least, node D, with the same circuit, we will begin drawing this out. From node D, we can see that we have two branches, R6 at 330 ohms, and branching the other way, in series, R5 and R4, R5 at 120 ohms, and R4 at 47 ohms, where we once again branch. into R3 at 120 ohms, and then R2 at 330 ohms in series with R1 at 100 ohms. Here we can see that we'll be verifying the series of R2 and R1, the parallel of R2, R1, and R3, the series of R5, R4, and the result of R2, R1, R3 parallel, and then the parallel of R6 and the result of the previous. So let's solve node D for the Thevenin resistance. Between R2 and R1 in series, we'll end up with 430 ohms. Taking R2, R1 in series, measured against parallel R3, gives us the result of 93.82 ohms. Then solving R5 and R4 in series with the previous answer will result in 260.32 ohms. Using that answer in parallel with R6, we can then find the Thevenin resistance, which is approximately 145.6 ohms. Verifying this in multisim, we can see that that was our result. Thank you for your time. This has been an overview on finding the Thevenin resistance in a circuit at multiple node points.